Because you develop software, I presume that you are familiar with threads. Multi-threading programming is harder than single-thread program because lot of things may go wrong, and when they do, it is hard to reproduce the same and hence harder to fix. But we must use it to get maximum value of multi-core processors. Those who develop apps in different platforms like iOS and Android, they know quite well that a lot of heavy lifting should not be thrown in main thread because this might hamper apps' responsiveness. Today I shall discuss what does thread safety mean, synchronization keyword in Java, race condition, code examples and how to fix it, object level locking and class level locking with code examples, few more discussions on synchronized keywords and performance hit for excessive synchronizations, few inbuilt concurrent data types locking mechanisms, and the last but not the least, some do's and don'ts in your program. When should you call a class a thread safe? A class may work great in single-thread environment. Its public methods may change its state exactly as intended in single-threaded program. Basically, it may always produce consistent state in single thread. This may be called as a thread safe class. But here what I mean is when objects or static members are modified or read from different threads, it should have inconsistent state. If thread A set the data as a 10 and thread B should read it as 10, if the program always runs in a single thread, then it's good, you are exempted from complexity. It is not bad to write thread unsafe class, but developer should document this, probably should write its usage to make thread safe, so that the client can do necessary work for writing a thread safe program using your class. The client doesn't always mean that it should be external. It might be you also. One of your class in your module can use another thread unsafe class written by you. Hence, it is very important that while developing you should know it's safe. No matter your class itself takes responsibility or any other class. Consider this program. Synchronized keyword is one such tool that makes a piece of code execute only by one thread at a given time. And this program is not thread safe, although it works great in single threaded environment. The problem is a problem with this program is that value of y is either 10 or anything else. This is classic example of race conditions. If the value of x is modified after the conditional check but before the multiplication by 2, then the result is different than 10. This may happen in real world. The thread which checks the value will get different value of y if another thread modifies the x after the check. Basically, x is a mutable data and it is being shared between threads. Here comes the locking. The program should be looking like this. Synchronization is a very popular way to make the code to be executed in single thread. Hence, this program works. Synchronized keyword automatically puts locks in its scope. It releases the lock automatically after its scope. It is important to understand that race conditions occurs because of thread scheduling algorithm, which is beyond our reach. OS usually handles that. Synchronization doesn't modify the order, rather it only ensures that the affected area doesn't get affected again. By putting synchronization, we are making the small program single-threaded, which also means that race condition will not occur in heavily synchronized class itself. Object level locking is used to synchronize non-static method or non-static code block on an instance of a class. This should be done to make instance level data thread safe. And this can be done as like shown in this program. When you do this, this instance is locked and accessed by one thread. A thread wanting to acquire lock in different method of the same object has to wait until the work in demo method is done completely. Class level locking prevents multiple threads to enter in synchronized block in any of all available instances on runtime. This means if in runtime there are 100 instances of demo class, then only one thread will be able to execute demo method at a given moment, and all other instances will be locked for other threads. This should be done to make static data thread safe. Use these two tools according to your context. These both have values. Many people have questions, so which one is better? But the question itself is not so valid in my view. But static variable is must to guard because it is shared among all. Singleton is one such example. To make singleton thread safe, you can also use class level synchronizations. However, there are a lot of different approaches towards making singleton thread safe. Now talking about few legacy things, synchronization had another one more important aspect in below Java 1.8. Without synchronization, a thread may not see the changes of the shared data by another thread, and that is true forever. All native data types except long and double are guaranteed to return a value that was stored into the variable by some thread, even if the multiple threads modifies the variable concurrently or without synchronization. But in practical, that doesn't work. Also, thread.stop is potentially dangerous method, hence was removed in Java 1.5 itself. It causes data corruptions. Hence, very popular method to stop thread is to request a thread to stop, and the thread should work accordingly. Basically, one thread polls a shared boolean variable whose value is changed by a main thread. Although this is very small program but very practical in real life. You get lot of camera frames from camera feed and want to process every frame. Maybe to draw something on a correct frame. Because your processing is very slow, you consume those frames slower than the camera produces. Hence, you want to store consumable frames to a queue and process slowly by a worker thread. But this should be done as long as camera provides frames. No matter you have unprocessed frames in queue. To mimic this situation, let's start the worker thread and let it run for 1 second by making main thread sleep for 1 second. Then request the stop by setting the boolean field. And you might think that because run internal loop should be terminated stopping the worker thread, but it doesn't happen in few machines depending on VM's implementations, be it JVMs or Dalviks or any other. Without synchronizations, the worker thread doesn't even see the changes in a boolean variable. So this is the correct version. Remember, you should synchronize both setter and getter. Synchronization in only one place, and that is true. That too in setter doesn't have any effect on it. If you make a declaration of m stop requested as volatile, you can safely remove the synchronization in both places. This is ought to mention that volatile only works in case of one thread writes or reads, and another thread only reads the same. Otherwise, use synchronization only. If you have noticed, M camera frames should also be synchronized because it is being shared between threads. It will be written by main thread and read by worker thread. Check out collections.synchronized list for this purpose, and otherwise you can use same lock for read and write. Java 1.8 created a class named read-write-lock itself for this purpose only. But let's say instead of using Java inbuilt concurrent data structures, you used your own locking mechanism to access same camera frames. This will definitely prevent from modifying a data structure by two threads at the same time and raise concurrent modification exceptions or be in an inconsistent state. But here comes another problem. Calling a function object from a lock state is one problem in concurrent programming. It creates a lot of deadlocks or bad data state. Let's say you have implementation of listener like this. Basically, once you get the frames inside the on camera frames method, you decide whether you should stop getting frames or not. It is quite valid that if you find your memory gone below 120 MB, you just decide to shut down worker thread, which in turn will stop submitting frames from camera because you are shutting it down from another thread. If you do so, you are in deadlock inside shutdown method because you have already acquired mlock in another thread, and you cannot get it right now, and it will wait forever in shutdown call. Fix is to move the code out of synchronized block, and you should not call function objects inside the lock state. So acquire lock for a very short time, exactly for what is needed, not more than that. The whole problem starts with the fact that read and write cannot be done at same time on a same collection. It is possible that while writing, copy the whole list and add a new entry. Actually, Java's copy on write array list is in such category, but mind its performance. Whenever you are in a situation to share mutable data among threads, synchronize it. But if your class is heavily synchronized, it will be single threaded by its essence. Hence, and this there will not be any race condition for sure, but you may lose opportunity of parallelism and impose delay. This is the only problem with excessive synchronization. Acquiring and releasing lock is actually nothing in terms of performance. When all the methods are synchronized or all of your code blocks are locked, one thread has to wait when when other thread is doing something on the same data. Think of a list of 1,000 elements that cannot be inserted in two indexes, say 10th and 99th, by two threads at a time when synchronization is heavy. And especially one lock is used for whole of the list. This is very bad. To achieve multi-threading support for this, you can use 100 locking objects and use for every 10 elements. This technique is called lock stripping, and same concept of using different locks in different parts of a class is called lock splitting. But all these techniques are for the same goal, that to minimize the locked code under same lock. Now, Java 1.8 has introduced a lot of lock classes and which are really very useful, like read write locks or reentrant lock, etc. Synchronization restricts JVMs or Dalvik VMs or even newest ART's code optimizations. So mind it while doing programming your Android also. So now few take home points. Acquire the lock and release as soon as you are done. Whenever a long running task is required, find a way to move it out of that lock. This will increase your lock time, hence better parallelism. Do not acquire lock unnecessary. Use Java's inbuilt concurrent data structure so whenever possible or in doubt. Look for java.util.concurrent packages and collections class reference like collections.synchronized collections. Increase immutability, possibly copy whenever a thread tries to modify a data structure so that the original data structure is untouched. Copy on write array list is such a class in Java. It copies its internal array of mutable operations like add, set, etc. It should be used in such cases where the list is rarely modified and often traversed. Do not lock entire object or entire class itself. Use lock stripping or lock splitting if possible. You should, but not always, prefer synchronization internally of your class. String buffer was replaced by string builder because string buffer historically almost always is used in single threaded program but had a lot of synchronization, hence bad performance. To avoid deadlock and data corruption, never call an Java function objects from within a synchronized region. Shared data must be synchronized even though you know that synchronization restricts JVMs or Dalvik VMs or even newest ART's code optimizations. If you have a reason not to use synchronized keyword as a tool of locking, use Java's inbuilt locking classes. Threads are reentrant to locks. One thread can acquire a lock multiple times even not releasing it, but two different threads cannot. Plus plus operator is not thread safe. That's it. At least this helped to gather data to look further. Thanks for watching.